Oh, so Ulf says that he's actually waiting. So he seems to be in the waiting room. He may not have.
I'm sure they will admit him like really soon.
And here I am. Hello.
Ah, there he is. Oh, whew, that was very cool.
Okay, so then we can start, everybody. Wonderful. Good morning and good afternoon to wherever you are. My name is Lale Koromdel and I'm excited to chair this NCME session today together with my colleagues, Professor Artur Pokropek from Poland and Janine Buchholz from Germany, Dr. Janine Buchholz. In contrast to the official NCME program where you can see 5 presentations, we will have only 3 presentations today, but I promise they will be amazing. And here I'm showing a slide where you can see which one of the 3 presentations we are presenting. All 3 presenters are calling from Frankfurt, Germany, I believe, unless they could escape the COVID-19 prison there. And we will end our NCME session with a summary and discussion by Professor Leslie Rutkowski from Indiana University. There will be a few minutes after each presentation for questions. So please post your questions in the chat room. During the presentations, Professor Pokropek will manage the questions and ensure that the presenters will respond to the most pressing ones. If you feel like your questions have not been answered, please feel free to email the presenters directly because we might not be able to answer all your questions due to the time limitations that we are facing. Please also ensure that your phones and mics are muted. Without further ado, let's get started. So I'll give the stage to Janine Buchholz.
Hi, everybody. First of all, thank you, Lale, for the neat introduction, and thanks to everybody else for joining us in this really interesting session on international large-scale assessments. So my name is Janine Buchholz and I work at DIP, and we here at DIP were involved in the operational work regarding the questionnaires in PISA 15 and 18. And the topic I want to talk about today is actually motivated by that work. I will talk about a comparison of multi-group CFA and IoT-based item fit for measurement and variance testing. Now, I'm in a lucky position that the paper with the analyses that I'm going to present today have been published in the meantime, so that you can actually read up on all of my findings and actually more than I'm going to present today in that paper that you can find on bit.ly ncme_Buchholz. So I'll first talk about the motivation and research interest, international large-scale assessments, of course, different methods for measurement and variance testing, and the research question. And I present you the study afterwards. I want to start off with the observation according to which international large-scale assessments often aim at comparing a large number of countries or education systems with respect to some latent variables. Here's a screenshot of a OECD report in which we see the results for a scale based on data from our questionnaire. It's enjoyment of science, and then we have this tabular way of presenting these findings with one of the columns referring to the mean score of that latent variable, enjoyment of science. And that kind of like inviting a comparison of these mean scores between these countries, right? And that's where the question of measurement and variance comes in. So whenever we want to compare our latent constructs, we have to make sure that measurement and variance holds. However, we see that measurement and variance is hardly tested, and if so, it is more likely with respect to the cognitive part of the assessment and not so often with respect to the questionnaire part or non-cognitive part. However, I want to make a case that these non-cognitive constructs are important too. First of all, we use that data for the population model, and also we find that secondary researchers really like to work with these scales that we provide in, for example, the public use file in case of PISA. Now, different methods or statistical methods, approaches for testing measurement and variance have been proposed in the past. This is only a short list, and I am going to focus on multi-group CFA and that IoT-based methods in the presentation. I'll talk about each of the two in the following. Multi-group CFA has been referred to as the one that's most commonly used. It's the one we often see in practice. And the test of measurement invariance goes as follows. We differentiate different models that represent different levels of measurement invariance. So these different levels are a configural level in which we assume an equal loading pattern for all of our groups, a metric level of invariance in which groups share the same slope parameter, and then a scalar level of invariance in which groups share the same slope and intercept parameters. Now, we then implement these models and compare their fits in the set of increasingly restricted models, and then by the change in global model fit, we would then arrive at our conclusion on the level of a particular or on a particular level of measurement invariance. Now, there are a number of problems with this approach. First of all, we found that these differences in model fit that we use when deciding among the different levels of measurement invariance were found to not hold in the presence of many groups. And then also, like, information on global model fit is typically not so much what we want, because like in the context of such large-scale assessments, we would typically more want to see where the problems are located, and we can get a more fine-graded information by looking at global model fit. So in the context of these multi-group CFA models, we can actually look at modification indices showing fits in the model if a particular item parameter constraint was released, and we can also look at the standardized expected parameter change to see how much that parameter would change. And these two measures of local model fit give us an idea of the magnitude and direction of that misfit in these restricted models. We have another approach which was operationally employed in PIAAC. That, to my knowledge, was the first like operational use, but that was for the cognitive part, and then for PISA 15 we started using it for the non-cognitive part also. In that approach, we started off with the generalized partial credit model, in which we assumed equal parameters across all our groups, and then calculated an item fit statistic for each group. In case of bad fit, we assign group-specific item parameters, and then replicated steps 1 to 3 until we have found acceptable item fit for all of our groups. Now, in addition to that approach being rather new, there's also a challenge in determining what an acceptable level of fit is. I already mentioned that we use an item fit statistic, RMSD. Here's the equation. It basically quantifies the difference between, or it quantifies the magnitude of the deviation of observed data from the estimated item characteristic curve. And it provides us, again, information on local model misfit. Here's a graph showing the item fit for each of our groups. That's a trick, actually. We calculate this item fit statistic for each of our groups, thus showing us which group's data can't be described by the item parameters that were derived based on data from all of the groups. And while this plot that you see right here looks actually quite okay, we see the interaction here. That's actually really interesting. So obviously on that item 13 here, for our greenish group, we see that obviously fit is worse. So there seems to be something going on in that data so that they can't be described as well by the joint model. In addition to that RMSD value that we referred to in our operational PISA work in 1518, we can also get a mean deviation index from that procedure, and that quantifies both the magnitude and direction of these differences. So, summing up, I just introduced two approaches for testing measurement invariance, while one is more known in our community and widely used. The other one is rather new, but has been employed operationally in that big and well-known context in PISA. These two approaches both give us information on local model misfits, both for magnitude and for direction. And I summarize these four measures here on that slide. However, these two approaches differ in a number of aspects. That is, in the underlying measurement model, in the nature of the analysis, and the level of analysis, and in the assumptions that we have about the nature of these indicators. And then, so the question would be, like, contrasting these two approaches, like, are they consistent in quantifying the degree of measurement invariance for a given data set? Or, to phrase it differently, would a researcher arrive at the same conclusion about the presence of MI using either of the two approaches? So we conducted a Monte Carlo simulation study and generated data under an ordinal response model for 5 items with 4 response categories each. You can see the specification here. And then for that data, we varied the type and extent of the measurement invariance violation. And here's some more detail on that. So we introduced these violations by adding a shift parameter on one of the items. And that gave us 3 total conditions. First is a baseline condition in which the shift parameter is 0, just meaning that all groups share the same parameters. And then we have a second condition in which groups differ with respect to their slope parameter. And that you can see here. And now we have a third condition in which groups differ with respect to their threshold parameter. And then we analyze that data under like both frameworks, the multi-group CFA and the IoT item fit framework. I shall mention that for the results I'm presenting now, I look at a multi-group CFA with the MLR estimator, assuming like a linear, assuming continuous indicators and a linear relationship between the indicators and our constructs. Here are the results on global model fits averaged across all our replications. And now, of course, we find that model fit in the baseline condition turns out to be best. And then it's worse when groups differ with respect to their slopes. And it's worst when groups differ with respect to thresholds. Here are results on local model fit for item 5. We see the same pattern, so modification indices are smallest in our baseline condition, of course, so these groups don't differ in these parameters, so modification indices are smallest. The same is true for the SEPC values. Sorry, I don't have that table here. We also see that, again, modification indices are worse when groups differ in slopes, and they are worst when groups differ in thresholds, and we see the same pattern on the RMSD. Now I show you results on the magnitude, or the indices quantifying the magnitude of local misfits in a visual form. And we start off with a baseline condition. So under both of these indices, we find that in the baseline condition, for all groups, the indices are very similar, of course, because we wouldn't find worse fit for any of the groups because they all share the same parameters. But now it gets interesting when we look at the condition in which groups differ in their true slope. We find that the modification index pertaining to the slope actually reacts as a function of groups deviating in the from the average slope parameter. And we see that the RMSD item fit statistic reacts too. And then when groups differ in thresholds, we see that both types of modification indices and the RMSD respect rather symmetrically around the average true parameter. Now here are the findings for the direction of model misfit. And I'm not sure how I'm doing on time, but I think I'm better cut this short and go to
you
my
have
last.
7 minutes.
Oh, we do. Oh, nice. Okay, so here are the findings for the measures on the direction of local model misfit. And we see, just as we would expect, that when groups differ in their slope, it's the slope-related modification index that would, oh, I don't think you see my cursor. Lala, do you see my cursor?
Yes, I do.
Ah, nice. Okay, so here we see that the slope-related modification index reacts. That was the same here also. But we see that these two indices aren't like completely independent from each other in the multi-group CFA framework. So they both kind of seem to react. But here it's a little clearer. And then for thresholds, we actually see a really clear pattern that the intercept-related modification index is sensitive to group differences in thresholds. And we see the same for the RMSD in the GPCM or IT framework. So summing up, we find a high consistency in quantifying local misfit resulting from violations of measurement invariance regarding an item's difficulty. It's less clear for group differences in the slopes. And I'd like to point out that for RMSD and MD, so the IRT, or the two indices resulting from the IRT approach, these are sensitive to both positive and negative deviations from the true parameter. So we saw a symmetric pattern there. In contrast to the GPCM approach, where both the modification index and the SEPC seem to only react to like really small discrimination parameters, which I found really interesting. So we could argue that so that would mean that these indices only show bad fit when a group's slope parameter is close to 0, but they wouldn't respect when a group's slope parameter was, say, like about 2, although that would mean that the latent construct is actually driven by that parameter, but we wouldn't detect it using these indices here. And then regarding the IRT-based approach, I would like to mention that we actually did find that the RMSD is sensitive to misfit in both the discrimination and the threshold parameter, while the MD or mean deviation seems to point only to misfit in the threshold parameter, which is something that was also observed by Lala's 2019 paper. Now, you might have noticed that both our analysis models differed from, both our data generating models in the findings I presented here differ from the analysis model. However, we did look at that and it's included in the paper. I cut it out here because the findings were really indistinct and kind of messed up, which is very surprising given that the ordinal response model was a data generating model. So we have a more solid discussion of that pattern in the full paper. In that full paper, we also looked at the data under like both of these approaches. The empirical PISA 15 data. And we actually saw like the same patterns, like a higher consistency in the magnitude of the indices for group differences in the thresholds. And then finally, I'd also like to mention the conceptual difference between measures of local misfit. So the RMSD is an item fit measure. So it captures actually just like general item misfit, but also group differences in an item's parameters. While the modification index captures only those like misfit, which is due to constraining that parameter to be equal with the other group's parameters. But still, it's kind of nice to see how they're not extremely far off. So to answer that initial question, like would we arrive at similar conclusions about the presence of measurement invariance? I'm not so sure about the absolute level, but at least we would find this, like under both approaches, we would more likely find group differences in items difficulties. So I guess that's good news. And with that, I would like to thank you for your attention and then point to the full paper again, which you can receive by following that wiki link here. Thank you very much. Here's the references, but
thank you so much, Janine, for your presentation. Arthur, are there any questions in the chat room?
Yes, thank you, Janine. I don't see any question, so you might you could ask some questions if you want. So please type. We have a couple of minutes, as we don't have any question from the public, I might have one question. So, Janine, so whether you have some special rationale under the choosing that the multi-group model will be treated as continuous, like the indicators will be treated as continuous. So why don't just compare the categorical data multi-group model? Because from these models you also could obtain the ME index and expected parameter changes. So I guess the same parameters for the continuous data. So I wonder whether
so first of all, we have both approaches in the full paper.
Okay. Okay.
But I decided to only include the continuous approach here because the pattern was a bit clearer. And also, I mean, that's a silly reason, right? I mean, first of all, I decided that it doesn't really matter because you have the full paper and you can just read it. Yeah. But another reason for just presenting the continuous model here, or findings from the continuous model here, is because I feel like we see that being employed more often, which might not be the best reason in the world either, but it seems just that people like to use the continuous approach for categorical data.
Well, it runs faster.
Say again more?
It runs faster, the model.
It runs faster. And that's actually, so for that empirical application that I was talking of, which is also included in the full paper, I did apply the ordinal model too, but we ran into too many problems because of empty cells. So we often had the problem that we have 0 answers because the distributions are skew. So we often had the case that we had 0 observations for some response category in some group, and then the model wouldn't run, and you'd have to collapse groups, and then it's just the silly.
But this is for weighted least square estimations, right? Because you could also use the
WLSMV.
Yeah.
And that, I think, for operational use becomes a real issue. Like when you have small samples and then like a very socially desirable scale, then nobody would. or it's less likely for people to choose like that. Strongly disagree or strongly agree box, and then you'd have these empty zone. And
yeah, but I understand. So the general message is like you have this approximation of linear indicators. They are working more or less the same as the categorical ones. Yes, yes, yes.
The findings are really mixed. So maybe one thing to notice is that both the modification index and SEPC reacted to both types of measurement invariance violations. So the pattern that we saw here, let me go back, like that we have differentiable lines here, that we didn't see so much. It was far more overlap for the ordinal model. So like, how can we phrase that? So releasing a constraint on, say, the threshold would seem to be as appropriate as releasing a constraint on the intercept. Sorry, I'm all messed up with the names here. So okay. It seems that releasing one of the
I'm so sorry for interrupting. I think we have to move on to the next presentation.
Thank you, though.
Thank you.
Thank you so much again, Janine. And I think our next presenter is Dr. Carmen Köhler.
Let me share my screen. Okay. Can you all see the presentation okay?
Yes. But you're
it's not yet in presenting mode.
We could see, but you need to enlarge it a little bit. Perfect.
Now you can see it? Okay. Oh. Okay. All right. So thank you everyone for joining this. Let me remove myself. Okay. Thank you for the nice welcome, Lale, and thank you everyone who is partaking in this virtual session. I am doing a comparison between a 3-level GLMM and the multi-group IRT model to detect group differential item functioning. So the main topic will be group diff as well. And my colleague Janine already introduced the typical method used in PISA and which is also used in PIAAC, and I will not go into much detail on it, but basically what is happening is that in the first step, we have a step of the scaling where the item parameters are constrained across all groups in a multiple group IRT model. And then in the second step, there is the estimation between the general item response curve or international item response curve that is based on all groups, and it is not very clearly visible in this plot, but it's basically the item response curve of the IRT model, and then we have the group-specific observed item response curves, which are these other curves here, and then the goal is to estimate the differences between these two. And this is done using the mean deviation and the root mean squared deviation. And in this presentation, we focus on the mean deviation, or in this paper that we are writing currently, because the mean deviation, since we don't have a square here as compared to the RMSD. The mean deviation also informs us about the direction of the deviation from the international item response curve. So this is the PISA approach, or what I will be referring to as the PISA approach to detect differential item functioning. And now to the second approach that we want to compare it to. This is a method proposed by Johannes Hartig, me, and another colleague here from DIPF, where we estimate a 3-level generalized linear mixed model, where we model here the probability that a person P in group G solves the item I correctly as the logit function of the ability level of the group, the ability of the person within the group, so the W is for within group and B for between group, and the difficulty of the item I in group G. Note that in this model we do not have a slope, so we differ here a little bit from the current PISA scaling approaches, which use the 2 item parameters, the difficulty and the slope. And here in this approach, we only have the difficulty of the item, which we will also be using in the PISA approach to make the 2 models as similar as possible. These 3 that I just showed here are modeled as random effects with the following distributions. And what interests us here the most is the vector of the average item difficulties, which is the B right here. And this is basically what corresponds to the international item difficulty parameter in the IRT model. And what also interests us here is the variance matrix of those difficulties. So what we have here are the correlated random effects with a joint multivariate normal distribution. And the variances themselves, so basically the diagonal of this variance covariance matrix, they tell us how much the difficulty parameter varies across groups. So large variances here, or high values of those variances, indicate that we have much group diff, because we have a lot of variance on that item difficulty parameter between the country groups. And what also interests us are the covariances, actually, or they could also interest us, because they tell us if there is correlated group diff across items. Put differently, items might show similar diff on maybe pairs of items. Like when we have 2 items with related item content, they might favor certain groups of examinees similarly. And these co-variances of diff, they might be important to model and not ignore in the model when diff detection is the goal. So that is the new approach that we proposed. And to sum up these 2 differences in the multiple group IoT model, we have fixed groups and fixed parameters. In the 3-level GLMM, we have random groups and random effects that we estimate. In the PISA method, we have no co-varying diff that is taken into account. but we do have that in the 3-level GLMM approach. In the PISA method, we do post-hoc diff analyses via the MD and the RMSD. In the 3-level GLMM, the diff estimation is basically part of the scaling model, because those variances, or the variance covariance matrix, is estimated as part of the model. In the PISA method, we do not really have definite cutoff values to identify countries with high diff. We also don't have that really for the 3-level GLMM. What we can look at are the residuals. So this is also kind of a post-hoc analysis where we can check if deviations from the international item difficulty parameter exist and how large they are, and can use them to identify countries with high differential item functioning. So the aim of our study was to compare these two approaches, test whether they lead to similar inferences, and maybe possibly combine their respective advantages to improve diff detection. Our specific research questions were: are the same items identified as items with diff? Do the approaches show similar patterns of diff covariances? And do they produce similar results regarding which countries show the most diff and which item parameters should be estimated freely in the scaling? So here's our method. We used the PISA data 2015 reading literacy. We simply chose the first 20 items. We used all countries with computer-based assessment, and we did a random selection of 500 students per country. So overall we had 28,500 examinees. And then we analyzed the multi-group IoT model. Like I pointed out earlier, the GLMM only estimates item difficulties. So in order to have the approaches as similar as possible, we used the 1PL here as the basis for the multi-group IoT model. And yeah, we did that in MDLTM. And then to estimate the GLMM, we used the LME4 package. And what interests us here is the MD for the diff detection. And here we are interested, like I said, in the variance covariance matrix of the item difficulties. This is a summary of the analyses we did. To answer the first research question, we compared the variances of the mean deviation and the item-specific variances, and we did this comparison per item. Then we also compared the covariances for both approaches, and then we compared the countries that were identified as countries with large diff using the two methods. So first of all, this is not a result of the comparison yet. It is just a slide to give you a better understanding of what it is that we are going to be comparing. So this is an example for one item. So you see here, this is item 6, and down here we also have item 6. And the method up here is the GLMM, and down here we have the MD for this specific item. And basically what you see here are the residuals. So the frequency is the frequency of countries. So each country has a specific place here on the x-axis, and I just chose Austria as an example because Lale is from Austria. So Austria is right here on this item. So this is the deviation of Austria from the mean general or international item difficulty parameter. And down here are the MDs, and we also have an MD for each country. And you can see here that Austria is also below this mean item difficulty parameter of the in the international or of the international item response curve. And when we correlated these two, we had very high correlations, which you can see up here. Yeah, so that was our first result. So the direction of the countries and the relative size of them correlate pretty highly using the two different methods. And now to answer the first research questions, we compared the variances and the item-specific variances of the the variances of the MD and the variances that we estimated using the GLMM. So the GLMM method is down here on the x-axis, and the MD is right here on the y-axis. So this is 20 points for the 20 items that we included. And you can see we have a correlation. It is at 0.44. So it's not perfect, and it basically means that in some instances, for example, this point down here, the GLMM method would identify this item as an item with a high variance. So we have a lot of diff on this item, and the MD method, so the PISA method, would not identify this item as an item with a very high differential item functioning. And also here we have some items where the MD would identify the item as high diff, and the GLMM would say it's okay. We do have some diff, but not the largest. So that was the answer to the first result. Then what we did in the second research question was to compare the covariances. And here we have the covariances of the MD. So basically we have the 20 items down here, and we have the 20 items here, and we simply correlated each item, the MDs of each item with each other item. That's what you see here. And you see that we have some clusters here. For example, the first 3 items, there seems to be correlated diff at the group level. Also here, we have some high correlations, and we compared it with the GLMM method. On first glance, it doesn't look very similar. This picture is much bluer, but this is actually an identification problem we still have, which the identification problem leads to overestimation, but a general overestimation of the covariances. So if you keep your eyes on like one area, maybe up here, or where we have a lot of blue, or maybe down here where we have some red, you can see actually that the pattern is pretty similar. So I'm going to switch back and forth a bit so you can do the comparison well. So the darker blue areas, they actually remain blue when we switch to the other one. And the lighter red areas, like maybe if you look here, lighter or slightly red areas, they remain light or turn a darker shade of red in comparison to the other.
Hi, Carmen, you have 2 more minutes.
Okay. I'm done in 2 minutes, so it's all good. So to answer the third research question, we compared countries that are identified as countries with large diff using the 2 methods. So we did per item a list of countries that were identified according to the PISA method as countries with large diff. And for the GLMM method, we used a standard deviation above 1. And then just had these 2 lists, and the PISA list was longer. Therefore, we checked whether a GLMM diff country is also part of the PISA diff country list. And for 11 items, that was the case. For 6 items, only 1 country was not in the intersection. For 1 item, it was 2 countries. And for 2 items, it was 5 countries where the method identified in, or the countries identified with 1 method were not part of the countries identified using the other method. To sum up, I don't really have a summary. I guess the summary is we do have similarities, but also some variations. Implications, maybe we could use the multiple group IRT model to identify anchor items and then use the GLMM method, simply because in the GLMM method we can take the covariant diff into account, and using anchor methods with this method, anchor items with this method actually makes the method much faster. In principle, the GLMM method is really time consuming. We do have problems with model convergence when we have a lot of items and too many groups. And another argument against the GLMM is we do not have discrimination parameter we can model, so the applicability to PISA data is a bit equivocal. What we are working on right now is a simulation study where we simulate various diff conditions in the data and explore which method performs better, to try and explain the differences between the results and under what condition which method performs better. Okay, this is my last slide. Thank you very much for your time and your interest.
Thank you so much, Carmen, for this very interesting presentation. Do we have questions from the audience?
Yes, we do. You already said a little bit about this, but also the question was asking to emphasize what are the advantages of using GLMM modeling. I don't know whether you want to say something more on that. Carmen?
Sure. Like, I think I listed the main advantage is really this taking the covariant diff into account, because we found in simulation studies we did on this approach is that when this covariant diff is not taken into account, then the diff per item might be biased when using the method. So there might be variance that is overestimated for 1 item or underestimated for 1 item if this covariant diff is not taken into account. And this is done in the GLMM model basically simultaneously. We do not first fix items across groups, but all is estimated freely or randomly. So yeah, that is the major advantage.
We also do have another question. Do you see the comment window, Carmen, or do you want me to?
No, because
Okay.
I think then you don't see the slides anymore. I don't know.
Okay, so for so the question is that for the GLM model, for GLM item D, variance is always positive. So in the sense that 0 is a boundary value, and therefore under the model, it's easier to obtain the results diff. So as I understand, the model is somehow implying the variance there, and whether this is the problem. Yes,
I'm not sure I completely understand the question, because the blue figure here, that's the covariances. So this is not the single variances that are overestimated per item, but this is the covariances that are overestimated. So yes, this would suggest too many, or this would suggest pretty large covariances of diff or of group diff. Yes, definitely. So we're still trying to work on fixing this identification problem. Yeah.
Okay, could I add something? Because it's happened that this presentation is a little bit, so I'm a little bit connected with this presentation. So first of all, I also like additional advantage that that from this modeling approach is, well, that this is the model and multi-level model, and you could probably develop it much more further than the classical diff measures. So for instance, you could, in some points, you could, for instance, add covariates to explain the diff, and by developing this model, you could probably learn a little bit more from the situation. Although probably you could also do this two-step approach with other measures, but it will be probably not so elegant. And also to responding to this question, so we do have some simulation studies. They have not appeared on this presentation, probably mostly because of my laziness. And what we know from the results that we already have, that in the when you have situations similar to PISA, those methods are actually working almost the same in general, big pictures. So the detection rate, the true positive and false positive rates are almost the same if you are looking, if you are comparing for mean deviation and root mean square deviations. So in general pictures, they behave very, very similar. Although I think that the GLMM approach is like interesting, because you could, in future, you could also incorporate additional things to this approach.
Yeah, thank you for the addition, Arthur.
Yeah, that's a pretty good point. So thank you so much, Carmen, for your presentation, and Arthur for your ads. So we need to move on to the next presentation, which is held by Dr. Ulf Köhler. Ulf. Ulf, you do not have audio. It looks like you are muted.
Yes, sorry, I will fix that in a second. Sorry.
Okay. Now we hear you.
Yeah, perfect. And I decided to keep, honestly, to keep in time, I decided to pre-record it. So let's see that you can hear it now. Welcome. My name is Ulf Köhler, and this is a pre-recorded presentation for the talk Validation of Extreme Response Style versus Rapid Guessing in Large-Scale Surveys. This presentation is joint work with Lale Coromdel, Frank Goldhammer, and Matthias van der Wier. Response style is a well-known phenomenon in survey research. In particular, for questionnaire scales and item batteries that are analyzed using item response theory, IRT model extensions that account for or incorporate response style are of interest. Two of the more recent developments are so-called IR3 models and mixture IRT models. Important goals of the response style models are to increase the validity of measurements and to improve the comparability of scores. For instance, IR3 models aim to separate individual differences in response style from a robust trait estimate that is less biased by response style. The rationale of IR3 models is the assumption of distinct decisions underlying the answering process of Likert type items. For a four-category item, the first response process is related to the decision between agreeing and disagreeing with that particular item. This first step results in a so-called binary pseudo-item with value 1 if the test taker's response is in the direction of an agreement. Subsequently, a second process is assumed for each possible result of the first process, which creates the tree structure. For both potential outcomes of process 1, either an extreme or a non-extreme response can be selected. This selection is conceptualized as a second process. More importantly, it is mapped again to an indicator variable that flags extreme responses, the so-called E-items. The coding of binary pseudo-items must correspond to the response process assumed for Likert items of a particular number of categories. In the empirical investigation reported in this presentation, we selected all 4 category Likert items from a large-scale survey. D items and E items are modeled in IR3 models using multidimensional IRT models. After creating the indicators and estimating MERT models using the indicators for extreme response ERS and responses in direction toward the trait DI, the latent correlation between the two factors in a two-dimensional model is of interest. A low correlation of the factors that correspond to the two process components of the IR3 model is expected if the extreme response style ERS is successfully differentiated from the trait response DI. If no dimensional structure is found for E items and D items, the unidimensional model will fit the data better. Accordingly, the single construct approach is applicable if two-dimensional models can be fitted to separate trait response and response style. An interesting extension to IR3 models is a combination with mixture IRT models, as introduced, for instance, by Rust et al. In 1996. The core idea of mixture modeling is to find subpopulations or classes of test takers in which an IRT model holds with specific sets of model parameters. Applied to the MERT models that are used to model the processes assumed in the IR3 models, mixture IR3 models are expected to find classes of test takers with different response styles as identified by using the D items and the E items as described above. The number of classes is unknown in advance. Information criteria such as the BIC can be used to select the number of classes based on model comparisons. A relationship between response style, such as extreme response style, and response time is known for non-cognitive and cognitive measures. However, typically only for cognitive assessments, very fast response times are used to identify what is known as rapid guessing behavior in cognitive tests. At the conceptual level, for each response, a qualitative difference is assumed for answers that are very fast and responses that are associated with a longer response time that would also allow for what is called solution behavior. For cognitive assessments, various research has shown that rapid guessing affects the validity of measures not only in large-scale assessments. For non-cognitive assessments, such as questionnaires, which are also often administered in large-scale surveys, Rapid guessing is not yet investigated routinely. The reason why research on rapid guessing in questionnaires is still in its infancies is that response times are not well defined if multiple questions are administered at one single computer screen. However, as shown on last year's NCME, identification of rapid guessing in questionnaires based on item-level response time thresholds is possible. Two things are necessary to investigate rapid guessing in questionnaires. The first requirement is to have item-level response times. For that purpose, we apply methods developed for the analysis of log data from computer-based assessment, namely a framework that rests on the definition of meaningful state and the use of finite state machines to process raw log events while extracting indicators based on states. In the application for extracting item-level response times from Likert-style item batteries, the method boils down to taking the difference between selected event types typically collected in computer-based questionnaires. The second critical component that is necessary to investigate rapid guessing in questionnaire scales is a reason to assume a qualitative difference between very fast responses and regular responses at different self-paced speed levels. Luckily, we observed in previous analysis using data from the PISA 2015 ICT Familiarity Questionnaire that individual level response times, as well as the aggregated answering time in non-cognitive measures, show a bimodal distribution as it is known from rapid guessing in cognitive tests. Response times that are very fast, meaning response times belonging to the first mode of the response time distribution, are labeled and flagged as rapid guessing. This requires to derive a threshold, and visual inspection of the response time distribution is used to identify the thresholds in this study. Flagging individual responses as rapid guessing allows to compute the number of guessed items for each scale. We will use this count to differentiate between engaged students, all students with no guessed responses in a particular scale, and disengaged students with one or multiple rapid guesses. We can also use a person level variable that corresponds to the response time effort RTE. The RTE is computed as the total number of responses not flagged as rapid guessing divided by the total number of responses. This variable is 1 for test takers that show no rapid guessing behavior, and an RTE measure smaller than 1 informs about disengagement. The computation of RTE is possible using flagged responses at the item level, but the measure might become a bit more stable when response times are aggregated within item sets. This is done by using the average answering time and a threshold identified for this average answering time measure for all scales that show a bimodal average answering time distribution. To illustrate the relationship between response style and rapid guessing, let's come back to the coding scheme for binary pseudo-items. The rapid guessing indicator at the item level is similar to the E items and the D items, an indicator variable that is created for each item. For that purpose, the item level response times are compared with the item-specific time thresholds. Since the MERG model is used to estimate the IR3 model, the item-level rapid guessing indicators can also be added as an additional latent variable. Adding the rapid guessing propensity to the IR3 model in the single construct approach results in a three-dimensional model that can be used to estimate the relationship between extreme response style and rapid guessing propensity, as well as between responses in the direction to the trait and the rapid guessing propensity. The overall research question in this study is to investigate if rapid guessing can be differentiated from extreme response style. We approach this question from three directions. Firstly, we use IR3 models and take a look how trait responses and response style can be separated in groups created by engagement. So we ask if the correlation between trait and response style is different for engaged versus disengaged students. Secondly, we use mixture IR3 models and search for classes with different item parameters in the binary pseudo-items used to model response style. In particular, we ask if the amount of rapid guessing is different for classes with extreme response style. Finally, we also take a quick look at the relationship between extreme response time measured as ERS and the rapid guessing propensity. Data for this study are taken from the PISA 2015 student questionnaire, and we selected all scales that used a 4-point Likert scale. We analyzed the subset of the Swiss sample, and we extracted the item-level response time measures from the log file data. For that purpose, we used the R package logFFM that implement the above-mentioned framework for the analysis of log file data. The IR3, MIRT, and mixture IRT models were estimated using the software MDLTM, and all IRT models were estimated as 2-parameter logistic models. The first descriptive result I want to report is the finding that we were able to identify response time thresholds at the item level using visual inspection. Bimodal distributions were found, for instance, for items of the scale SD094 for all items, including the first item, for which the item-level response time measure also includes the time for reading the stem. As expected from previous work using data from the ICT Familiarity Questionnaire, we also find for the PISA student questionnaire that the average answering time follows a bimodal distribution. By aggregating the rapid guessing behavior within persons, we clearly see the expected gender difference in the response time effort. Male students show a lower RTE, and we again find language differences in the RTE using the test language, which was either French, German, or Italian in the Swiss data. I will now continue and present the results regarding the 3 research questions. In research question 1, we inspected the correlation between responses in the direction toward the trait and extreme response style measures. For that purpose, we estimated 2-dimensional IR3 models and compared the information criteria to unidimensional models. For the total sample, as well as for the subsample of engaged and disengaged students, we found the 2-dimensional model fits best. We found a similar result for all scales, but for the scale SD012, which was added as a marker as this scale was using an anchoring vignette. Taking all together, the IR3 models can be used, and extreme response style is found also for disengaged students. We found no hint that response style is only present for engaged or disengaged students. The scatter plot shows for each investigated scale the latent correlation between the DI and the ERS factor. On the x-axis, the result from the subgroup of engaged students is plotted, and on the y-axis, the correlation estimated in the disengaged group is shown. As can be seen, the correlation for the disengaged students is closer to 0 compared to the correlation for the engaged students. On this slide, I present a first result from the mixture IR3 models. For the example scale SD094, AIC and BAC point to either the 3 or the 4 class solution. Inspecting the category frequencies shows that for the 3 class solution, the plot in the lower left part of the slide, no clear extreme response style can be identified. In the 3 class solution, extreme responses are observed mainly in class 1 and class 2. In the 4 class solution, the plot on the lower right part of the slide, extreme responses are more clearly grouped in class 1 and also in class 2. Without going further into detail with respect to the interpretation and labeling of the classes, I want to emphasize again that the mixture modeling was applied to the DI and ERS items only. Hence, it is not necessarily the case that we also can expect differences between classes in other variables such as response times. However, the difference between classes becomes obvious already with respect to the average answering time. As can be seen by a visual comparison of the median, the classes that contain the extreme responses are the classes with the lowest average answering time. The most obvious answer to the question if the amount of rapid guessing is different for students with extreme response style can be seen for the 4 class solution with respect to the engagement measure computed as response time effort. Mixture modeling of the IR3 indicators seems to identify classes of test takers with extreme response style, and the test takers in these classes show lower test-taking engagement in terms of RTE. The same result also holds for the number of guessed responses per scale. Regardless of the 3 or 4 classes, both solutions identify one class with notably more guessed items. I will now briefly describe how this result generalizes across all selected scales. For that purpose, we generated this large plot. Each row corresponds to one selected scale, and each dot represents the average number of guessed responses in one class. We plotted the best fitting solution with respect to PIAAC, and the first row, ST094, corresponds to the results shown on the previous slide. Inspecting the remaining scales shows us that for many, but not all scales, a similar picture can be observed. Although the mixture modeling was implemented with respect to the binary pseudo-items of the IR3 approach for modeling response style, the classes identified with respect to the item parameters of this IR3 model also differ with respect to the number of guessed responses. I will now briefly report the relationship between the latent guessing propensity and the response style as measured by the E item and the trait response as measured by the D items. For that purpose, I compare 3-dimensional models with different 2- and a unidimensional model. For all scales, with ST012 as the exception, the 3-dimensional model was the best fitting model. As you can see on this slide, however, rapid guessing propensity within scales is only for some scales correlated with either response style or the trait response when analyzed across all test takers with a latent trait model. To summarize the findings. Up to our knowledge, this is the first study that deals with the relationship of rapid guessing and response style. By comparing groups with different engagement levels, we have shown that engagement measured as rapid guessing affects the relationship of extreme response, ERS factor, and responses in the direction toward the trait, DI factor. We found hints that the correlation between ERS and DI seems stronger for engaged students. We found no substantive difference between using a global response time effort measure compared to scale-specific indicator such as the number of guessed responses. The mixture IR3 model for ERS and DI identified for most scales a class with higher average number of guessed items. That means classes in the mixture IR3 model can be validated with respect to the engagement differences. The classes that contain test takers with more extreme responses seems to contain also test takers that show more rapid guessing behavior. Across all test takers, we found separate factors for the tendency for extreme responses, ERS factor, the rapid guessing propensity, and the latent trait factor. However, we found only weak correlations between extreme response style and rapid guessing propensity. The presented study comes with a couple of limitations. The mixture modeling for many scales requires, for instance, a more careful interpretation of the solutions. The superficial interpretation across scales was only conducted to report findings that, to some extent, generalize across scales and maybe represent a stable finding. Response style was modeled using IR3 models, but other psychometric approaches to investigate response style might provide additional insight. Moreover, since investigating rapid guessing behavior in questionnaire scales is a rather new research field, some arbitrary decisions could have impacted the findings, so replication is strongly required. Finally, further studies should go beyond the single-scale approach and investigate response style across different items together with rapid guessing that is expected to be more prone in scales administered towards the end of the questionnaires. To close, is extreme response style different from rapid guessing? Yes, we showed that both phenomena can be empirically distinguished, but response style and rapid guessing are related and overlap. Consequently, Further research should develop models to investigate both phenomena simultaneously. Thank you very much for your attention. I'm looking forward for your questions and comments.
Thank you so much, Ulf, for your interesting presentation. I do not see any questions in the chat, and just in order to have enough time for Leslie to do her discussion, I would suggest that we immediately move on to Leslie's discussion. And if any questions pop up in the meantime in the chat, Arthur will monitor and we will get back to the questions after Leslie's discussion. Leslie is actually an expert in the area of large-scale assessment, and she has extensive experience in analyzing large-scale assessment data. So we are really happy that she has time to join this NCME session today, and we are very excited to hear her point of view on the three presentations. So Leslie, please take over.
Thank you. Thanks a lot. Thank you, first of all, for inviting me to discuss this session. And I know we're all sort of tired of online interactions, and I was a little bit skeptical about how this might happen, but I think the quality of the presentations were excellent, and the attendance is much higher than you typically see in a live session. So I think all in all, this is really a very nice experience, and I was very happy to be a part of it. So I have some written feedback that I'll share. And first of all, this was a nice collection of papers that delves into measurement quality issues, and especially including issues around measurement and variance and response times. And issues around data quality are always important in any kind of survey. But as studies like PISA expand, and they bring in participants like Cambodia and Zambia and Honduras, a good understanding of cross-cultural differences is really critical. One issue is that these countries are very, very different than OECD countries when PISA was first developed. That was the concentration. And these newcomers to PISA tend to have very substantial economic, cultural, and geopolitical differences. Cambodia, for instance, still deals with the consequences of the Khmer Rouge, where somewhere between 1.5 and 3 million mostly educated or skilled Cambodians were executed. And this has ramifications 50 years later. Another example is in the case of Honduras, where murder rates are among the highest in the world. And extortion is a common funding source for gangs, with students, teachers, and schools frequently being victimized. At the extreme, there was one private school near the capital city that was believed to have temporarily closed due to extortion demands. And these kinds of issues make the assumption of equivalent measures a real challenge. And although the above examples are definitely not comprehensive, they're representative of the types of methodological and logistical difficulties that are attributed to developing and administering a comparable instrument to large numbers of increasingly heterogeneous countries. So that's just sort of an opening statement about the importance of this work and how challenging it is to establish equivalence and to understand different processes across countries. So first of all, on the Buchholz and Hartig paper, it's really fortunate that it's already published, but I really can't offer much in terms of feedback that might sway what you do, but I enjoyed reading the paper very much. In terms of, you noted that there isn't a whole lot of RMSD work going on, but I just wanted to point you to a co-authored paper that I did with Jesper Timstra, Maria Bolsanova, Linda Lau, David Rakowski, and myself. And one of the findings is that the RMSD, the properties of it, make it such that in very low performing countries where there's enormous positive diff, it can't be detected. I mean, it could be infinitely diffy and we can't pick it up. Janine, you spoke a little bit about this, and so I won't focus too much on it, but I was just wondering a little bit about why you only presented the linear CFA results. One suggestion, and again, that's published, so, but maybe for next time, it would be nice to see the AIC and the BIC for the CFA-based results, just to have, you know, some kind of way of comparing the two. The figures were beautiful. I found them to be really informative and very helpful in understanding what was going on. I think this is a great example of smart graphic use, and it's interesting to see that the general pattern across the measures holds. I was kind of surprised that the ordinal CFA model, I mean, given that this is essentially the generating model, didn't perform very well on the standardized expected parameter change. And I wonder if we have time, Janine, if you have some thoughts on why that might be the case. One thing that I was curious about, especially in light of the paper that I worked on with with colleagues on the RMSD, is that you presented the generating model for theta, that it was normal for the mean, that it's 0.5 for variance, and that the variance is distributed as 0.8, uniform 0.81, 0.2. But I didn't see how that actually worked out, or maybe I just missed it when I read the paper. So I'm wondering a little bit about what was the range of theta for the simulation, and especially how does that range of theta compare to the various item locations? And then with the next paper that was presented by Carmen Köhler with Koremel, Hartig, and Popkopek, it's a constant struggle to find a good measure of diff internationally, and I think, you know, I'm already speaking a little bit about that. But I think it's really encouraging to find that these methods are being developed and compared. I mean, from, you know, back in the first sort of modern international assessments, where diff was basically just eyeballed. You'd look at the response function internationally and then look at it for an individual country and say, oh yeah, it's pretty close, good enough. To these more formal measures that give us a better objective way of evaluating diff and non-invariance. So I really like to see this kind of work developing in a more systematic and a more methodologically principled way. And as I said in my opening statement, as these studies grow and the countries grow in terms of the differences, a faster, more accurate, more efficient way to identify substantively relevant measurement differences is really important. What I think would be great to see is if there were maybe like a special issue or a volume where this paper could be combined with Janine's work and other related things to see who wins the horse race in these different diff measures, that there could be a sort of systematic comparison to get a good understanding about what works best. And I think one other thing is that it would be nice to see a balance of the performance of the methods with the relative operational burden of these methods. So, you know, maybe a method works better, but if it takes so much more time and it's operationally so much more burdensome, is it worthwhile? So an analysis, a kind of economic cost-benefit analysis of the accuracy or the effectiveness to time-cost trade-off. And then I very much agree about future directions. I think it would be great to see this via simulation so that you can get a good idea of how the methods compare at finding the truth, and especially for low performers, like I said, where it's really hard if there's positive diff to ever be able to detect it with the RMSD. And then the final paper presented by Ulf Krone, I really liked the recorded part of it. It made it very smooth and very easy to understand. And I appreciate that the session had a mix of studies where it wasn't just the cognitive side that was a part of the analysis, but also that the background questionnaire is examined. And I agree that it's a very important part of the assessment. And it's important to understand if we can tease out if extreme responding and rapid responding are different phenomena, because we know that they occur, and it calls into question the validity of the results. So getting a sense of how overlapping these are and how differentiable they are is important work. One question I have, if we get time, and Ulf, if you could respond, is how comfortable are you with two processes? And I saw at the end of the slide that you had an alternative way of looking at this in terms of more processes. So are you comfortable with the assumption of two processes, and do you feel safe about assuming that? And you talk about this being kind of an arbitrary choice in terms of where you set that cutoff, and okay, fine, it's arbitrary, but the results look reasonably convincing as far as where you're going to make that threshold for rapid responding. I wondered a bit about the classification of disengaged as being just one item below a time threshold is adequate. And do you expect that your results might change if this cutoff was more stringent, maybe 2 items or 3 items, especially on longer scales? And then I think in slide 41 to 42, I'm seeing what I'm going to ask about, but maybe you could confirm this. It would be interesting to see if any of this depends on reading proficiency. So are poor readers more inclined to rapidly respond? In some work that I'm doing with colleagues, we see a little bit of evidence of this, that poor performing students go very quickly. And then one last comment, which is just some information that I've learned recently, is that the PISA timing data has some issues. There was a glitch in data collection, that total time on an item may not actually be total time, that it's a return if someone returned to an item, then it's the last time that they spent on the item. And we have to be a little bit circumspect until the data are the total time data are harvested, because we don't really know the extent of the problem or the impact of the problem. And this is really relevant in our understanding of rapid guessing. So if rapid guessing is actually a kind of change behavior after a student thinks about it, and we're assigning this, and this might be some of the way in which you're able to differentiate these two processes, because if it's actually change behavior, then we're maybe making some substantial mistakes. And I think that was all I have.
Thank you so much, Leslie. This was great. This is great feedback. This is great insight. I think this is super helpful. And I would like to give the authors now some time to respond to your questions, and maybe we can start with Ulf, since he did not have any question time after his presentation at all. And also thank you so much for mentioning the issue with the PISA 2015 response time data. I think that was an important note. I don't have any details about this other than it might only affect very few cases. But again, you're right, like, fingers crossed. So it might not have a big impact at all, but you're right, we definitely have to, as soon as the database is updated, we have to go back and check the analysis again and run everything again, just to be sure that we're fine. But thank you so much for pointing this out, for example, also for other people who are using the data. Okay,
yeah. Maybe I can take over and say, there will be very likely no problem with respect to the glitches of the total time in this analysis I presented. And this is because I extracted the time information from the raw log event as collected by the platform. So I didn't use the OECD or the ETS prepared total time measures. And the final state machine method to analyze log file data is capable to treat revisits of pages and screens. And I'm aware that there are a couple of things going on, but we tried actually and worked quite some years on the PISA background questionnaire timing log data. And I'm quite confident, but of course we will reanalyze as soon as we understand more about the problem. The second question, or the first question, was how sure are we with respect to the number of processes? And I think this is kind of the first attempt to relate these two areas. And I think that I'm planning to submit for next year's NCME an attempt to combine both things. So a process model that includes guessing as one process, and then extreme response as a second and a third maybe step in the process. And I think at the end it boils down to how to compare across different process formulations and how to learn which of the hypothetical processes will be the most likely one. And then there was the question how to define, is one rapid guessing enough to call a scale a rapid guess scale, or should we collect two? That's actually the reason why I added the discussion point to say, oh, well, we have a couple of arbitrary decisions and not yet very well established methods or strategies. So again, the process data are available at country level. So when you want to replicate such analysis, I do have an R script that can be used to extract the country-specific process data, and then please try to replicate, and then let's find some common ground how to model rapid guessing in questionnaires, because currently there are more data than we have papers or analysis or researchers working on that. And that also applies for the last question, though I think the cutoff values are to some extent arbitrary. And I think the next step will be to have at least more exploratory work to understand the relationships, which is hard to present at conferences because it's still just looking at figures and graphs and try to get a grip on the data. But that is the next step. And as I think it's not the same, but it's related, so it might be worth to investigate to understand the relationship a little bit better.
Thanks, Ulf. That's really helpful.
Okay, so we have like 1.5 more minutes. Maybe Janine would like to respond to Leslie's comments.
I feel that was just minor technical remarks, so I'll get back to you maybe with an email. So maybe we can give that last minute to Carmen though instead.
Sure, Carmen, do you have any comments?
I didn't write down any specific questions that I could answer. I really liked your idea to make like some sort of a cost-benefit analysis, because I see your point that that one method was extremely computationally burdensome and the other was less so. So yeah, I'm not quite sure yet what all we need to include in that cost-benefit analysis, because yeah, one might be much better in, for example, detecting diff in low-performing countries and the other is not, and then does that outperform the computational burden that we do have for that? So I think it's kind of difficult to really set these, yeah, what do I call them? The parameters for what in the end do we decide for, but definitely we should yeah, keep in mind how much effort a method takes. Yeah.
Maybe one of us knows someone who has to write a dissertation.
Okay, great. So I think we reached our time. So at this point, we would really like to thank the presenters for sharing their valuable research. We would really again like to thank Leslie for taking the time to discussing those papers and giving us new points of view to think about. And also thanks to the audience for joining this NCME session, for taking the time to listening and for your questions. And yes, enjoy the rest of your day, enjoy the rest of the virtual NCME conference. I think it's great that it's happening. I also would like to point your attention to a comment from the NCME staff in the chat room. They are sending a link because they want to evaluate how we see the whole process in a survey. So please, if you have time, take the time to respond to that quick survey. And we really hope to see you in person next time at the next NCME if possible. Thank you so much for joining. Have a great day and hope to see you soon. Bye-bye.
Thanks, Lala.
Thank you.
Thank you. Bye.
Thank you for